Hello, my name is Sammy Houghton, and for my final project, I investigated water consumption data for campus buildings at UNC to see what factors may contribute to a building's high or low water use. The goal would be to use this insight to target conservation efforts in buildings with particularly high water usage, or emulate features of buildings with low water usage so we can save even more water across campus. For a little bit of background about why I became interested in this topic, last semester, I interned with the UNC Facilities Energy Management Department, which does a lot of work with monitoring water and energy use in campus buildings. They were interested in identifying buildings that had high water use intensity, which is a building's water usage divided by its square footage, and were particularly interested in looking at water use efficiency within different building types. A building type might be a classroom, a lab, a residential building, etc. And a high performer within that type would be a building with a lower water use intensity, WUI, than its peers, and a low performer would be a building with a higher WUI than its peers. Including building square footage and building type is important for water use efficiency analysis because they provide context for a building's water usage, since bigger buildings probably tend to use more water than smaller buildings, and building types will use water differently. All of my data were provided by UNC Facilities in Excel spreadsheets, which were converted to CSVs to be processed in KNIME and R. The main dataset included over 50,000 records of monthly water meter data for several UNC buildings from 2007 to 2018, with attributes such as meter read date, consumption amount, building type, etc. I also received a spreadsheet from the energy management team with buildings' yearly energy usage and square footage, which were used to calculate the water use intensity values and energy use intensity values by dividing total energy use or total water use by building square footage. For additional supplemental data for each building, I downloaded a dataset from the UNC Planning Room website, which lets users create reports by selecting different queries. The main field I was interested in was a building's construction year. I started out cleaning my data in KNIME, but quickly realized I needed a little bit more flexibility in order to manipulate the attributes the way I needed to for clustering, so I ended up doing the majority of my data processing in R. The basic KNIME cleaning I did do included converting the billing date attribute to a date-time variable, pulling out the year and month from the date-time variable to create new columns, and removing rows with meter read errors or duplicates. Finally, since the focus of my research last semester was on indoor potable water use, I decided to filter out the records that were from irrigation and non-potable water meters, since they tended to have more missing values and errors, and I was not as familiar with how to handle errors in those datasets. My first R script filled in gaps in the time series meter data. If a building was missing a consumption value for a particular month in a particular year, I used the average of that month from other years' readings for that building. Once the data was cleaned, I created WUI profile vectors for use for clustering. At the building level, each building had a vector containing its average WUI values for every month of the year, resulting in a vector length of 12 for 222 buildings. The year-level WI profile vectors also consisted of 12 values, but there were 13 times as many vectors to be clustered since there were 13 years' worth of data. Instead of monthly averages, the vectors consisted of actual WUI values for each month of the year for a given building. The final set of R scripts I wrote were to determine the performance level target variables for buildings by going through each building type, normalizing the WI values, then marking rows with the normalized WI value greater than 1 as a low performer, and those with values less than a -1 as high performers, since these values fell within the top or bottom 16% of WI values for a particular building type. I used the k-means algorithm to cluster building WUI profiles, and using a combination of DBI index evaluation and visualization evaluation, I determined the optimal cluster number to be 4 at both the building and year level. Some problems with this analysis were that there were a few buildings with particularly high WUI values that greatly influenced the clustering algorithm. However, when I ran the algorithm with higher k values, the clusters towards the bottom tended to overlap with each other even more. Even so, I did include a more detailed cluster analysis in my building level classifier by using the results from a k value of 8 just to see if it made a difference, but in the end the model that used the results from the cluster algorithm with a k value of 4 had better performance. And here's the yearly clustering analysis for value. The building level classifier, I used the random forest algorithm and ran over 30 different combinations of attributes using leave one out cross-validation. As you can see on the slide, the random forest classifier results in a pretty complicated decision tree, so there's probably some risk that these models were overfitted. Total model accuracy results ranged from about 0.67 to 0.833, and attributes in the model that resulted in the highest overall accuracy included a building's yearly average WUI, monthly average WUI, square footage, building type, and clustering results. For further evaluation, I wanted to maximize recall for low performers because one of the project goals was to identify as many low-performing buildings as possible and to maximize precision of high-performing buildings because we want to be confident that the buildings we identify as high performers are actually high-performing buildings if we're going to emulate their practices. Unfortunately, none of the building level models were able to classify any high-performing buildings, likely due to a lack of data since there were only 9 instances of high-performing buildings. Interestingly, though, an attribute that greatly improved the recall of identifying low-performing buildings was the building's WUI average for the month of August. Perhaps this is due to the changing population on campus at the start of the fall semester. I included a time series analysis component in my month and year level classifiers by adding lag WUI values as new columns for the random forest algorithm. The accuracy statistics were much higher than they were for the building level classifier. This is also probably due to the fact that there were many more data points available to train and test the year and month level models. At the monthly level, I used 2 different approaches. The first was to create lag values for a building's previous 3 months of WUI values, and the second was to include the same month from the previous 3 years as the new lag columns. In the end, both of these methods resulted in similar overall model accuracy, around 0.97, but using the previous month or months resulted in higher precision of identifying high-performing buildings, whereas using the previous year's values resulted in higher recall of identifying low-performing buildings. At the yearly level, it turned out that the time series data was much more useful for identifying high and low performing buildings, and overall model accuracy ranged in the 0.96 to the 0.97 range. The month level classifier definitely did a better job of identifying high performing buildings than the year level and the building level classifiers, but the yearly level classifier had higher accuracy when only the previous year's WUI value were used and not the past 3 years. So just to wrap up, I wanted to say I learned a lot by doing this project, especially how important it is to clean your data, to understand how to handle missing data, and how difficult the art of clustering can be. I also wanted to point out that the way I created my target variables may have introduced some bias, since I used building type in the process of determining high and low performing buildings. That obviously ended up carrying a significant weight in the most of the predictive models. I want to continue exploring different target variables for water use efficiency, but I feel like this experience was a good start. Some other extensions for this project I would like to do would be to include latitude and longitude data in the classification by performing a geographic weighted regression, which I read about in Contra Costa and Jane's paper. They applied it to multifamily buildings. And I'd also like to add more data from other universities to make it a more robust model. Finally, I'd like to go beyond classifying building performance at a given point in time and try to identify events such as a building changing performance levels or identifying significant changes in buildings' overall water usage. Thanks so much for listening, and I look forward to hearing my other classmates' projects.